light involved. So yeah, the first problem says, consider the diagram and indicate clearly the position and nature of the image formed by the mirror. Draw rays corresponding to the light coming from the open circle and mark any relevant angles. All right. So first thing, redrawing the diagram as always. So we have some sort of an object with a circle. Oops. This should be a straight mirror. And then we have the observer. So the first thing they say they want is the image formed by the mirror. And they want the position and the nature. So in these problems, it's usually good to even underline the exact things they want, because they don't want us to just draw the rays, but answer specific questions which don't end with a question mark. So pay attention to that in order not to lose easy marks. But yeah, so how an image is formed from this circle, we have rays going off in all directions, and they reflect from the mirror and go up in all directions. But some rays will go to the eye. So this is a relevant ray, which we can draw. And they say they want any relevant angles. So what's important for flat mirrors is that we have an angle of incidence, then we have a reflective angle. And we know that for a flat mirror, the angle of incidence would be the reflective angle. So make sure you make this very clear and very obvious in your solution. So the image isn't formed by a single ray. You need two rays crossing, and these could be the actual rays or the extensions of the rays. In this case, we can see that the actual rays will go off in different directions and won't cross, but there are extensions into the mirror. So the ray coming here and then straight line down will all coincide in one point. And this is the reflection of this circle right here. So we can draw our image like this. So let's go back to the problem statement. Indicate clearly the position and nature of the image formed. So the nature, this, because it's formed by the extension of the rays, would be a virtual image. The position, it's symmetric with respect to the flat mirror. So the distance from here to here is the same as the distance from here to here. And it's also flipped. Yeah. Draw the rays corresponding to the light coming from the open circle. We have that. And mark any relevant angles. We have done that. So yeah, just make sure you go back and you check you have everything you need. Is that all right for this first problem? Okay, I don't see anything in the chat or Q&A. If something comes up, even if later, just shoot and I'll go back. Yeah, okay. So next problem. A parallel-sided slab of medium B and refractive index is sandwiched between two slabs of medium A. And then a beam of light goes from A to B and then into A. And they ask, given us an angle, what is the angle to the normal of the light beam in A after it has left B? Okay, so the situation here is that we have three different regions. Have region A, region B, region A again. And light goes from the first A through B into the second A. We can draw that. Let's say the light is incident here, then it gets refracted because it goes into another medium. And then it gets bent once again as it goes outside into A. All right, so this is the path of the light beam. And then we have a few relevant angles. So they give us the angle of incidence, which is just theta. Then afterwards, we have theta, let's call it theta B. We're after this angle, the angle at which the light emerges from region B. So let's call it theta final. Very quick question in the chat. What would this angle be? Just to make sure everybody's following and what I'm saying is fine. Theta, the same as the original angle of incidence, the original. No, so I see a couple of right answers. So theta B. What I'm asking is, so in this medium, the light doesn't change its direction, like it doesn't get bent as it goes through B. So we know that this is a straight line. And we have something at the right angle here, right? And something at the right angle here. So these are the normals to the surface. And given this angle, which is theta B, we're asking which this angle is. We know that these two lines are parallel because they're perpendicular to lines which are already parallel. We have it in the problem statement. There is a parallel slab. And this is why we can translate this angle to here and know that this is theta B. All right. Ask me in the Q&A or in the chat to explain this again if it's not clear enough. Just quickly look at the chat again. Okay. Okay, so we have all our angles and we're after this one. So usually, okay, somebody asked, can you explain it again? Sorry. Yes, of course. That's what I'm here for. So let's look at this region. So this is region B a bit more carefully. So the light comes at this point. So it has come from here. It doesn't matter. And this is the normal to the surface, because this is how we define angles, right? And it gets bent. So it continues. So this is not one line. It gets bent. It continues at some angle, which we define as theta B. When it reaches the other surface, it gets bent again with respect to another normal to that surface. And say it bends like this. Again, it doesn't matter. And we're looking for this angle. What I'm trying to show you is that this angle is defined as the angle between this line and this one. And this one is normal to this side of the slab. This angle is defined as the angle between the same trajectory of the beam and another normal. However, this other normal is perpendicular to a line which is parallel to the other side of the slab because it's a parallel slab. Just checking the chat. Oh, I think people were just thought that I was asking for theta if, okay, just in case. So yeah, translating this angle because of the parallel lines, you get theta B, right? Okay. So in order to get theta F, which is the final angle we're after, usually when we have refractions and we have the refractive indices, it's easiest to write Snell's law. So in this initial region, we have that the refractive index there times sine theta, which is given, equals the refractive index in this region. So we're looking at this point here, times this angle. And then looking at this point, we can write a very similar equation. And this time, for this side, we have this refractive index times the sine of the final angle we're looking for. But you can notice that this thing is the same as this thing because they're in the same region, which means that NA times sine theta equals NA times sine theta final. And because both angles are in the region between 0 and 45 degrees, that means that if the sines are equal, that the angles are equal. And this is our answer. Chat. Yeah, okay. Questions here? All right. Hopefully this is okay. Then we have problem 3. In this problem, we have a parallel beam of monochromatic light initially traveling in a direction above the horizontal enters a region of atmosphere in which the refractive index increases steadily with height, and which of the graphs represents the path of the beam of light. So first things first, how is beam traveling? Initially, it's monochromatic, so it won't spread out, like all of the light will bend together. Good. They say initially it's traveling in direction above the horizontal. It's not entirely clear which the direction is, but all of the answers you have, all of the plots start like this. So this is the vertical height, this is the horizontal direction. So all of the plots start like that. So obviously we can assume that the light is traveling in this direction initially. And then it says the refractive index increases steadily with height. So a steady increase in height, we can break it down into increase in height step by step. So we can break down the atmosphere into a number of these slabs, regions. And if the refractive index goes like that, we know that N1 is smaller than N2, smaller than N3, etc. So this is what the atmosphere looks like. Now, one way to look at this is to simply write Snell's law. So N1 times sine theta 1. So if this is incident at theta 1, then it will emerge in some direction theta 2. Oops. And we know that N2 is larger than N1, which means because sine is a growing function, that theta 1 would be larger than theta 2. And this would mean that as the light goes in, it gets bent towards the normal and even more towards the normal at the next point between two refractive index regions. And so we can see that it gradually bends towards the normal. And if you make these regions infinitely small, you get a smooth transition. So something, for example, like D wouldn't be the option because you're told that the refractive index changes steadily. Chat, what do you mean when you say that sine is a growing function? So I mean that, so if this is sine theta, this is theta, this is what the function looks like. And here is 45, this is 90 degrees, this is 180, and so on. And with angles, we're looking for angles between 0 and 90. So, this angle can only be up to 90 degrees. It can't go to 180, otherwise the light would be coming from upwards somehow. And we can see that for a larger theta, the sine is getting larger, and this is why we can make this conclusion, because technically the right follow-up from this line would be that sine theta 1 would be larger than sine theta 2. But if our angles were in this region, a larger sine would mean a smaller angle. And this is why I'm specifying it. Sometimes they like to put traps like that if you're working with, for example, 90 to 180 degrees angles. So maybe keep it in mind, but in most cases, especially with refraction, it's simply, if a sine is bigger, the angle is bigger. But yeah, keep that in mind. All right, so this is using Snell's law. Just a very quick, I don't know, way to remember that, just because it saves me time usually on exams, is imagine a car. It has two wheels, is going in this direction. And if this is the large refractive index, say this is sand, so it's a very dense surface, and this is smooth asphalt. So when this wheel reaches here, it will start going slower than this wheel, which will be here, because it will still go on the asphalt. So the whole car will kind of tilt towards the normal. And while this wheel will only move slightly in the same amount of time, this will catch up with it. And so the light will bend towards the normal. Just a way to remember that without thinking about maths. But if it's better for your brain to do maths, yeah, feel free. Questions? No? All right. And something in the chat. So which letter was it? The answer. So the answer is B. Because somebody liked my car analogy. The answer is B because I never ended up drawing it. But as I said, because this refractive index is bigger than this one and this is bigger than that one, the light will start going towards the normal more and more. And so it'll start bending upwards, or yeah, towards the vertical normal. Right. Okay. And then problem 4. Narrow beam of light is incident normally upon a thin slit. The light that passes through is spread out by diffraction. Have something in the Q&A. Okay, I'm gonna go back to that in a bit. So problem 4, the thin slit is then put into water. The beam of light is shown the same way. And they're asking whether the spread of the diffracted beam is bigger or smaller. How does it compare to the spread in air? So, first things first, if we just have a single slit, and let's say the single slit is of thickness D, and we have a wavefront of monochromatic light coming towards it, what happens in diffraction is that in classical optics, each point of that slit becomes a secondary source of the so-called wavelets, so wavefronts of light, which leads to regions of, as you can see, constructive interference and destructive one. So the light, the intensity of the light you see on the screen is not just like a fixed spot, but more so it spreads out to the sides and it has like a lower intensity rings around it. I'm not entirely sure what is in the syllabus and what is not. The others, please tell me if I'm giving way too much information. But maybe it's good to have just seen that. How we define the position, for example, of the first minimum here would be that the size of the aperture, size of the slit, times this angle here, so the angle at which we're looking compared to the incident light, is equal to m, which is just some integer. This is plus minus 1, plus minus 2, etc., times the wavelength of the light. So maybe what's important to remember here is that the spread of the diffraction, so this is this theta, is proportional to the wavelength. So this is how diffraction is dependent on the wavelength of the light, and the wavelength of the light is dependent on the medium through which the light travels. And if this is not obvious, it's because the speed of light in any given medium is given by the speed of light in vacuum, so c, 3 times 10 to the 8, over the refractive index of the medium. So air, we take the refractive index to be 1, so it's the same as vacuum. But in water, the refractive index is slightly larger, so the speed is slightly lower. On the other hand, for any wave, we have that the speed of that wave equals the frequency of the wave times its wavelength. The frequency is fixed. The frequency is only determined by the source of the wave. It has nothing to do with the medium. So the frequency is fixed for a given wave. The speed, we agreed, is this. So here the speed of light is in vacuum is fixed, but what changes in the refractive index. And so we can see that the wavelength of the light is proportional to 1 over the refractive index. Good. So what we can say is that the refractive index in air is smaller than the refractive index is in water. So this is 1 and 1.3, but it doesn't really matter. This means that the wavelength is inversely proportional to that. So the wavelength in air is larger than the wavelength in water. It gets stretched out. And from here, we know that the dispersion would be larger for larger wavelengths. And so the dispersion we get in air would be larger than in water. And looking at the answers, we have answer C, which says less spread out than in air. So yeah, so this would lead us to answer C. Initially, when you look at the answer, the first one is the same as in air, which, like, yeah, it should be obvious that it can't happen just because the light changes its wavelength. The diffraction will not occur in water, also should be removed at the first scan, just because there is no reason for diffraction not to happen in any medium. And then figuring out whether it's less or more is the actual part of the work. Does it all make sense? In the meantime, somebody asked, do we need to know how to draw ray diagrams and about real and virtual images? I think so. I think it's on syllabus. Let's see what Anna replies, just in case. But yeah, you do usually get problems which ask you to draw out where the light goes, how do you form the images, what type the images are, and so on.
I was just going to say that they're also really helpful. So yeah, exactly what you said.
Okay, good, yeah. But yeah, whenever you have linear optics, draw out things, even if they don't specifically ask you for it, because they are helpful. All right. Questions or? If there's anything else, I'll just stay and reply in the chat. So I think we can move on to the more involved problems.
Excellent, thank you, Nina. Yeah, as Nina was saying, if you've got anything left over with those couple of questions, do put something in the chat and Nina can have a look at it, or put it in the Q&A and she can answer it there. Maybe that's easier. Right, on to the next set of questions then. Elle is going to be taking you through the next few questions. Elle, you ready to take it away?
Yes, I am. Can you see my screen before you disappear?
Yep, we can see your screen just fine.
Perfect. Okay. So here is a few more ray diagram type questions. So the first part asks for an observer at A seeing the image of P reflected in the mirror Y. So when we have questions like this with reflections, the main thing to remember throughout is that the angle of incidence is always going to equal the angle of reflection. And so that's basically the only concept we're going to need here to start with. So I'm going to try and sketch this as best as I can. So my light is going to go up to the mirror and then be reflected back up to the observer at A, so that the observer can see the image. And then when I do this, I'm always going to label here. I'm just going to label here that this is theta and that this is the same theta. So if my diagram isn't to scale or isn't looking great, I've made it clear to whoever's looking at my work that the two thetas are equal because the angle of incidence equals the angle of reflection. And then the next part of that asks us to sketch, draw a ray from P to the observer at A and mark R the position of the image. So as Nina did, to find the position of the image, we are just going to, so let me just draw this parallel line. So to find the position of the image, as Nina did, we're just going to extrapolate the visible ray that leads us to A back until it crosses with the light coming from P. So that's this point here. So all we've done there is extrapolated our light ray that goes to A back through the mirror to see where our virtual image would be created. And I'm going to do a similar thing for the next part. So if that doesn't make sense, I'm going to do a similar thing for the next question. So for part B, we still have our observer at A, but this time they want to see the image from Q. So in the same way, we're just going to take our light ray that's going to come off Q, and we want the one that's going to bounce, reflect. Oh, I'm going to just maybe do a better job of that. So we're going to come from Q, and we want it to reflect with the same angle of incidence as the angle of reflection up to our observer at A. And then I'll label that maybe theta B and theta B, but I'm still making clear that those two thetas are the same as each other there. And then similarly, to find where our image, our virtual image S is going to be located, we're just going to take our line straight from Q and then find our light ray that's going straight to A and just extrapolate that backwards until it intersects with our line from Q. And then I'm going to mark that on there as our image S. So, is there any questions on what I have done there? So all the concepts we're kind of using here is that the angle of incidence is the same as the angle of reflection, and to find the position of a virtual image, to find the position of the virtual image, we just extrapolate the rays backwards until they intersect. Do you need to label the angles for the virtual images? No, the question doesn't ask you to label angles. I'm just not very good at drawing diagrams. So whenever I can, I'll try and be like, these two things should be equal, or these two areas should be the same, so that there's no ambiguity if my diagram causes any ambiguity. So in optics, we have two kinds of images, real images and virtual images. Virtual images are the ones that are found by tracing the real rays. So this is a real ray. This is a real ray. By tracing two real rays back until they intersect. And that's where a virtual image would appear. And so that's the sort of thing that you'd get in a lens or a mirror. Like a mirror, you're always getting a virtual image because we're having to extrapolate these real lines back to where kind of like they don't, I guess, exist. They're just, we extrapolate them until we find the position that they intersect. There's probably something good on BBC Bite Size about the difference between real and virtual images and where you can find them in different cases. But I hope that makes sense. And if not, I'm sure Anna and Nina will type something in the chat for you. Okay, so we'll go on to our last part of this question, which asks for, so an observer at B can see an image of P resulting from reflections from both mirrors. Draw a ray of light from B to P, which enables this image to be seen. So if I'm going from B to P, and it's reflecting off both mirrors, I think my first ray from P is going to come downwards at least some. So if I try and sketch down to about halfway down between like this. So my ray is going to go down to hit mirror Y and then similarly reflect off mirror X. And then I need it to get to B. So let's try and sketch that on. So we are reflecting off mirror Y, and then that reflected light is going to reflect off mirror X in the way I've done with all of them, because I'm not very good at diagrams. Theta, I don't know, we've not used theta alpha, and then theta beta, theta beta. So again, I didn't have to label those. I just wanted to make it very clear to whoever's looking at my work that theta alpha and theta alpha are the same, and theta beta and theta beta are the same. So that's how we get to observe something at B. But now we need to find the position of any image formed. So to do that, as we've done before, we are going to extrapolate this light ray out. And the same thing, we're going to extrapolate the light ray from P out. And then this is when you wish you'd drawn a better diagram, but I'm going to extrapolate this out as well. And at some point, because the lines aren't parallel, at some point they're going to converge over here. But obviously, I would shift my diagram to be able to draw that a bit better. And that is the position of the image that's formed. So all I've done there is extrapolated the real light ray that is going towards B and the real light ray that's coming away from P. And I'm just finding the point in which they intersect, which is the point at which my image would be formed. So please let me know if there's anything there that doesn't make sense. Okay, I'm going to move on to question 6. Again, keep putting anything in and we can sort it, but let's go for question 6 now. So question 6 is a fisherman listening to the radio on the bank waiting for fish. So fishermen by a bit of water. The sound is also heard by the fish and the path of the sound waves entering the water is shown in figure 5. So I'm just going to make a quick sketch of figure 5. So we've got the light ray going in and we've got it bending away from the normal. So let's just make that very clear that that's bending away from the normal, and there's my little fish. The top one is air and the bottom one is water. So the first part of the question asks us to describe what happens to the frequency, wavelength and speed as it moves from air to water. Can everyone put in the chat what quantity is invariant as we move between mediums? That was one of the hints. So what quantity do we think is invariant as we move between the two mediums? Yeah, look, all the answers come in so far, looking great. Yeah, it's the frequency that is invariant. So that's what I'm going to start by describing. I'm just going to say that the frequency does not change. That's our first point. And then next we're going to look at how the speed of sound changes. And there's two ways we can kind of think about that. if we look at our diagram that they've given us, we can see that as we enter the water, the sound waves bend away from the normal. And bending away from the normal tells us that it's moving faster. So let's say bend from normal, bend away from normal implies moving faster. So we know that the speed of sound the speed is going to increase as we enter the new medium. So I'm going to say speed increase. And we can think about that physically, because as the sound waves move from air to water, and we know sound is just a way we describe the vibrations of molecules. So sound propagates through the vibration of molecules. So if the molecules are closer together, like they are in the water, then the sound is going to travel faster. Which is why, I don't know if you've ever noticed, but sound waves travel faster in solids than liquids. They travel the slowest in air, then a bit faster in liquids, and then a bit faster in solids. So we can deduce either from the diagram or the physical intuition behind it, that the speed is going to increase in the water. So then from there, we can use our trusty C equals F lambda, where C is the speed and F is the frequency. So if C increases, that implies that our lambda, our wavelength, must also increase, as F we know is a constant. So if the speed is increasing, we know that the wavelength is also going to increase. So that's a little argument behind part A. And then we see that the fisherman has got a speaker that has got two sources. Let's mark on here and here the two sources. And it says, sketch a diagram illustrating how destructive interference between the sounds from the two speakers can occur when the radio is playing a single frequency. So this diagram that I started to draw here is looking a bit reminiscent of Young's double slit, if you've seen that before, because that's basically what we're going to do here. That's what the argument is going to be for Young's double slit. We've just got two separate sources of waves, and we're just going to see what happens when they interact with each other. So we're going to have one, so trying to bear in mind that the frequency and the wavelength of this wave is supposed to be constant, and also the amplitude, just because we're moving through a single medium, but my diagram isn't great. And similarly, we're going to have the same frequency and wavelength coming up from this second source. The two sources are going to interact, and at the point in which they are in antiphase, so when one's trough coincides with the other's peak, that is the point in which we're going to have complete destructive interference, and you're not going to be able to hear anything at that point. So here is a diagram that I found earlier, in case mine didn't work out, and we can see at this point that this one's peak is at the same point as this one's trough. So when we superpose those waves and add them together, we're going to get zero amplitude at that position. Let me just check the chat and Q&A to check we're okay. Yeah, so frequency is a constant because it is determined by the speaker itself, and it isn't affected by the medium it's in. Sound waves travel faster through water and solids than in air, but electromagnetic waves travel faster in air than through water and solids. Yes, that is what Nina showed as an example with light earlier, that bent towards the normal, and then in this one, in this case, we're bending away from the normal as we're entering the new medium. So I hope that clears that up. Okay, so then we have part C of this problem that says, for a note of a single frequency and for a given separation between the two speakers D, what is the maximum wavelength lambda and orientation of the radio for complete destructive interference? So the condition for destructive interference is that the path difference between the waves, and I'll explain what that is in a second, is a odd number of half wavelengths. So let me write that down. So what I mean by that is lambda over 2, 3 lambda over 2, 5 lambda over 2, etc., but not like 2 lambda over 2, 4 lambda over 2, which is just lambda and 2 lambda. So we need an odd half integer of a wavelength. So those are the examples that we're going for. And path difference is just the extra distance that one of the waves has had to travel than the other one. And as we can see, this bottom wave is going to have to travel further to get up to the points that we're talking about because it's on this angle rather than going straight across. So the path difference is going to be this odd half integer, which I've expressed as 2n plus 1, which is just an odd number, over 2 to get an odd number over 2 times lambda. So the maximum wavelength is going to be given by, so we need to work out what d min. To find the maximum wavelength, that would coincide. So lambda max would be when d is minimum. So to work out when that would be, so let's work out when d minimum would be. And in this case, we're going to say that the path difference is of the same order of magnitude as d, so that I can use this equation here, which is the equation I'm familiar with. So d min is going to be approximately the path difference. They're going to be of the same order of magnitude, and for this kind of estimate that we're doing here, that's what we need. So to find d min, that's going to d min is going to be when the path difference is the smallest, and to get the smallest path difference, it'll be when n equals 0. So the path difference equals lambda over 2, and that gives us d min, because the path difference is going to be approximately the separation between them. And this is the case when the two waves are what we call coplanar with the center of the speaker. And all that means is, in my diagram I've got here, if these are the speakers, two waves are going to start on this same plane as the center of the speaker. They're going to be, it's not going to be on an angle. It's going to be when the speakers are pointing forwards perpendicular to the plane of the speaker. I'll just check if there's any questions. Can you draw the diagram with wavefronts? So if I was to try and draw the same diagram with wavefronts, I guess I would get something that looks like this. And I don't think I could illustrate in the same way these are the points of constructive and destructive interference. I think it is made clearer with the curvy diagram like that, because then I could draw the one underneath, and we'd be able to easily identify that this is the bottom of this. This is the trough of the top wave, and then this is the peak of the bottom wave, and that when they superpose together, when they add together, we'd be able to see that we get 0 there, whereas I don't think it's as clearly illustrated with the wave fonts, so we would try and stick to these kinds of wave diagrams at the right. So why is the path why is the path difference the same as D? Well, they're not the same. We're just going with the same order of magnitude, because if we were to kind of like try and work out this distance that the top wave has traveled versus this distance that the bottom wave has traveled to get to this point, we would do some form of, so if I just call this x1, and we call this x2, we would do some Pythagoras to work out what D is in terms of the path difference, and the path difference the path difference is x2 minus x1, so let's just call that path difference. So to work out what D would be, we'd do some Pythagoras, because we're going to assume that that's, so we'd say D squared plus x1 squared equals x2 squared. So D squared equals x2 squared minus x1 squared. And because we're looking for this approximation, we're going to make the assumption that that is approximately x2 minus x1 squared. And obviously we know this isn't the case always, which is why we can say that D is the same order of magnitude as path difference. So I want to make it clear here, I'm making an order of magnitude estimate rather than making trying to find it out exactly, because that would be quite difficult. So all we're saying is that the path difference is approximately the separation between the two speakers to start with. Okay. Does this work the same? I'm sorry, whoever's just asked a question in the chat. I'm not sure what you mean by that. Maybe that's me just not reading it properly. So if anyone minds having a quick read through that for me and trying to respond, that would be great, because I'm conscious that time's getting on and I want to get on to the next question so that Anna has lots of time with her questions that are quite complicated. So I'm just going to move on to 7A, but please keep asking your questions and we'll keep working on them in the chat. So 7A explains that the intensity decays as one moves further away from the source due to the rays diverging. If I is the intensity and R is the distance from the source, then I is proportional to R to the N. What is N? Well, we know that if the intensity is decreasing the further away we get, N must be negative. It must be some form of I is proportional to 1 over R to the something. It needs to decrease as R increases. So this is related to a bunch of other laws that have a similar form. And this is an inverse square law. So can maybe people put in the chat what other examples of inverse square laws have you come across? So things that are proportional to 1 over R squared, which is, we've got the decay as things move apart, and then it's not decaying like linearly. We've got an extra factor. Next, this is the intensity of light, gravitational attraction, and electric potential charge. The forces from gravity and two charges together, they all have inverse square laws. So that's great. So it has this similar relationship. And the next part says, if the intensity, okay, so it gives us an expression for the intensity. Oh, it says intensity is proportional to I naught lambda m Rn alpha to the 6 1 plus cos squared theta. So that is our expression for what intensity is proportional to. So what we want to do here is insert a dimensionless constant of proportionality so that I can write this as equals, and I'm going to insert k, and this we're going to say that k has no dimensions. It's just going to be some scalar number, could be 2, could be some decimal, but it's going to be a scalar. So now we need to substitute in the units that we know. So we know that I is going to be, so we know that I and I naught are going to have the same units. So we can say I equals I times, so we need the units of lambda to the m. Well, lambda we know is going to have the units of length, so length to the m. R we know is a distance, that's also going to have the units of length, and we're going to insert n equals -2 that we worked out in the previous part. And then we've got alpha to the 6, and we know from the question that alpha also has units of length. So we've got that. And then we know that 1 and cos squared theta are both dimensionless. They're both just going to be numbers. So we've got nothing to add there. So from there, we can say, well, any units from I are going to cancel with the other units from I. So their units are going to cancel. So we're just left with m -2 plus 6. The units of length are going to cancel with the units of length on the other side, and the units of length on the left-hand side are 0. So then we can say that m plus 4 equals 0, so m must equal -4. So the relationship of intensity to wavelength must go like lambda to the -4. So it must massively decrease as a wavelength would increase. Okay, I'm just going to check the chat and the Q&A. So the orientation of the radio, you just say the waves are collinear with the center of the speakers. So the waves are coming out like parallel to the speakers, perpendicular to the like normal, which I'll illustrate in this diagram. Up here, so this is the center of the speaker here. The waves are collinear, so they're coming out this way. So the I'm just going to use what Anna said. So the n equals -2 comes from the fact that the light spreads out in a sphere, and the surface area of the sphere is proportional to r squared. So if we think about a point source, the light's going to spread out like this, and the intensity at every point is going to be inversely proportional to the area that you're spreading it out over. So there's going to be some fixed amount of like power, some fixed amount of energy that is going to be spread out over some area, and as the area increases, the intensity at each little point on that sphere is going to decrease. So it's going to be proportional to the area, and we know that area is proportional to r squared. So as the sphere gets bigger, there's going to be less like energy concentrated at each point because it's being spread over a larger surface area. Okay, I think that's everything from me. Please keep putting stuff in the chat and Q&A, and I will continue to answer as Anna talks us through the next 2 questions, if that's okay.
Cool. Hi, everyone. I will just share my screen. Would someone be able to tell me if you can see whiteboard?
Yeah, looks good.
Yeah.
Cool, thank you. So the first question, we have a glass prism of refractive index n is 1.4, has a triangular cross section with two angles of 45 degrees. So we can draw that. We have this glass prism, and these are both 45 degrees. And this is floating on some mercury with its largest side facing downwards and a vertical depth of 2.5 centimeters submerged. So it's kind of in this mercury. Sorry, that's a terrible rectangle. And we know we've got this height h submerged, and this is a side of length L, which is 45 centimeters. So what we want to know is we have a monochromatic beam of light entering the glass parallel to the mercury surface. So it's going in like this. And it internally reflects off the bottom face of the prism due to the presence of the mercury. So we know that because the mercury has a refractive index of 1.4, that's greater than air. So we can, oh, and it must in fact be greater than the glass of the prism. So then we have this reflection. This kind of goes like that. And we have the beam refracting towards the normal because it's going into a more optically dense medium. And then, so it's doing this reflection down here. And then it's reflecting out of the prism, and here it's kind of going into the mercury. But what we want to know is what the maximum height is above the mercury surface such that it can leave on the other side of the prism parallel to the mercury surface. So actually, excuse me, what we can see is that I've kind of drawn it too high here because it's bouncing off and going into the mercury. And if we drew it lower, it would reflect sooner and therefore come out in air. So we can see that the limiting case is going to be when it is reflected right on this surface. So now I'm just going to erase that and redraw the limiting case so we can draw on all the angles. I might try and draw some better straight lines while I'm at it. So we've got this prism. I wonder if I can use the straight line tool. Wow, look at that. Amazing. So there we go. Whole new world of drawing. And it's in this mercury. And we have the light leaving. Maybe I'll draw the light in a different color. The light's leaving along this surface. Oh, and move it. Okay, I'll just draw the light normally. It's leaving along this surface. So we can kind of go backwards, draw the reflection. Coming in like that. And we know that it came in parallel here. So we can draw on the normals, and we want to start to know some angles. So can anyone tell me in the chat what this angle of incidence would be? (45°). Nice. And that is because we were told in the question that these two are 45, which I forgot to draw back on. But yeah, you're all on it. So this one's 45°. And then we have theta r here. And we can call this angle here delta. And it's reflected again at delta. And then because of the symmetry, we can see that this angle here, because it's reflected by the same angle, this one here, theta r, will also be over here. And then we've got Snell's law where n1 sine theta I is n2 sine theta r. So we can see that this works both ways. So if it's approaching the boundary of the glass at theta r, then it will be it will emerge at theta I, which is, as we've been told, 45 degrees. And then we can see that if I draw on briefly in red, we have two similar triangles here. Sorry, that's terrible, and I will remove it in a second. But you can see that these are two similar triangles, which is going to be really useful. And what we'll do is we'll label the different lengths. If the total length here is L, if we call this length B, then this length will be L minus B. And we can call this height above the surface big H, because in the question we were given this, which is little h. And in the question we're given that little h is 2.5 centimeters. And we're trying to find big H in this limiting case. I'm just going to check Q&A in the chat. Why does the ray refract down instead of refracting up? Okay, so if I draw, say this side's the glass and this side's the air, then as Nina explained earlier, we have the light coming in, and I think she used like a car. So we've got these two wheels here, and say, well, the air is traveling faster in. So this wheel's going to enter the glass and suddenly start traveling slower, but this wheel's still traveling faster. So it kind of turns the ray. I think Nina probably explained it better, but that means that it turns down because if we draw this normal, it would emerge here if it carried on in a straight line, but it's been turned this way, so it kind of refracts towards the normal. And I'll just check the chat. No, all good. That's just you all telling me it's 45 degrees, which is brilliant. So now we're going to do some similar, well, actually first we'll use Snell's law to calculate what theta r is. So here we've got n1 sine theta I is n2 sine theta r. We know the angle of incidence is 45 degrees. So sine 45 is equal to n2, which we're told in the question is 1.4. And I think I mistakenly said that that was the refractive index of the mercury earlier, so sorry about that. And sine theta r we don't know. So if we rearrange and plug this into our calculators, hopefully we will find, well, you can tell me in the chat, what do you find theta r as? We've got a 30.3. Any more for any more? 30.3. Very nice. Oh, and a 30.34. Yeah, so just because I want the answer to be very precise, I'm going to keep theta r to 2 decimal places. So we've got theta r is 30.34. Just erase this little diagram here. So what do we need next? Next, let's find delta. So with this big triangle, we know that the normal is at 90 degrees to the surface. So we've got 180 degrees. The internal angle of the whole triangle is equal to 45 plus 90 plus theta r plus delta. So who can tell me what delta is to 2 significant figures? Sorry, 2 decimal places. 2 significant figures is not enough. $14.66. Nice, well done everyone. So we've got 14.66 And so now I'm just going to redraw these two triangles to make the next bit a little bit easier. So I will draw them underneath so that hopefully we can still see the whole thing. So we've got this. Oh, okay. That was going so well before. There we go. Got this triangle here. And then next to it, the littler one. And we can label on this triangle the stuff from before. So this is L minus B. This is B. The height of this one, we can see would be big H plus little h. The height of this one is just little h. And what I'm going to do is I'm going to call this top angle alpha. And so that's just 90 plus theta r, which I won't make you do in the chat, but we'll find that that's alpha is 120.34 just by adding 90. So we've got alpha 45 and delta, and then the same on this side because it's kind of the same but reflected. And we're trying to find this big H because that is maximum height of the incident beam above the reflected surface to still get it coming out this side parallel as we want. So we're going to use some similar triangles. So we'll call this side C. And we can see that C times cos 45 is equal to H. So then we know that the side of the length C is equal to H over cos 45. Please put in the chat if you don't understand where this has come from. Just check the Q&A again. I'm confused. Which triangle has these four angles? Okay, I will draw again on in red, just so we're looking at these two triangles here. I'll leave the red on this time because I've drawn them again below. So that's got the 45-degree angle here, the 90-degree angle here between the normal and the side of the prism, the angle of refraction here that the light ray goes through, and then delta, this angle here that it's reflected by. And then same on the other side, delta, theta r, 90 degrees here and 45 degrees here, which gives us similar triangles, which is hopefully going to be very useful. And in the chat, right, yeah, where do 45 plus theta plus delta add 180 on the diagram? Okay, cool. So that's here. So this triangle, the internal angles add up to 180. And that's equal to this 45 plus this 90 plus this theta r plus this delta. So hopefully that helps. And Delina said, isn't it sine 45, even if they are the same? So yes, you're right. And I'm also right because you're right, they're the same. So I can use cos 45 here because it's kind of, I don't know if you've been told like the cozy rule, so they're next to each other, so it's cos. But you're right in that if I hadn't drawn that on, we'd use sine because it's here and they're not next to each other. So because they're the same, it doesn't matter. We can argue it both ways. In the Q&A. Why is the reflection of the ray at the boundary of Mercury and prisms symmetrical? So it's symmetrical because it's reflection. So that means that we're coming in at this angle delta and we're going back out at this angle delta. So it will hit, because the prism is also symmetrical. So these two sides are kind of the same gradient but opposite. That means that it will then hit this side at the same angle. And so we have the same angles on each side. I feel like that wasn't a great explanation. I hope that helps. It's not a 90-degree triangle, so how can you use cos and sine? Yeah, okay, so I use the 90-degree triangle here. So that's that's to get this side length C from H, because H isn't actually a part of this triangle that we're using at the moment. So now we're going to use the sine rule to help us get this side length B. So from the sine rule, we have that C over sine delta is equal to B over sine alpha. So if I just move all of our bases to the other side, we'll then find that B is equal to sine alpha, which is 120.34, times C, which is H, over cos 45 times sine delta, which is, where's it gone? 14.6. So hopefully we will find from that that B is equal to 12.06 centimeters. And I'll just check the chat again. You guys say alpha? Oh, this is alpha. Cool. Yeah, so just explaining the right angle triangle. And I think I explained the reflection being symmetrical. And I'll explain about marks and stuff. Or maybe one of the other panelists can guess how many marks this question might be worth. It's one of the longer ones that'd be worth a bit more, I think. So now we've got B and L minus B, and we're going to use a little shortcut because these are similar triangles. So we're going to use that. Well, hopefully you know that you can use like this side over this side is equal to this side over this side because they're similar triangles. But we're going to cheat and use that the height over the base. No, sorry. The height, this height divided by this height is the same as the base divided by the base. And this is also true because of similar triangles. And if you do it the other way, you get the same answer, but it will just be a little bit more complicated. So this then gives us that H plus H over little h. So the height of the big one over the height of the little one is equal to the length of the big one over the length of the little one. And so we'll rearrange this. Slightly running out of room, but hopefully we'll make it. So we have big H is little h times L minus B over B minus little h, which then comes out at 4.33 centimeters. But you guys can check for me if you like in the chat. Got your calculators handy. And okay, yeah. So someone says, I don't understand where the numbers have come from, the 12 centimeters. Okay, so the 12 centimeters was over here. And that came from all of these and also H being 2.5 centimeters, which I missed out. I didn't write at the top, sorry. And what else? I think it's okay. Yeah, I think I was just helping. I would like to get such a tough question too. Is this a timed question, or will they maybe break it down into smaller sections? So this is definitely a tough question. It took me a while to work through it, and I've done 3 years of physics. So yeah, it would be a tough question, and I hope there'll be a fair few marks for it, and you're definitely not expected to fly through it or get all the way through it. It's just about trying to draw a clear diagram, trying to work through a little bit at a time. That was part A. And I'll now have to erase quite a lot of this to move on to part B. So hopefully, well, there's a recording as well if there's anything I've written down that I now rub out and you're panicking because it was helpful. I'm trying to leave the key drawings on, which is why I'm erasing everything painstakingly by hand to make a bit more space. Oh, I've removed the bottom of the tank. We'll just pretend it's still there. So now we've got the prism is then placed on top of a different clear fluid of the same density and floats. Because that means that it's submerged by the same amount. What is the maximum refractive index of the fluid that will allow the light to travel along the same path as in part A? So we can see that the path it's traveling along in part A is reflected here. And so key to this is going to be total internal reflection. So if I write down Snell's law again, who can tell me what theta r would need to be for us to have total internal reflection? At what point is it kind of not being refracted anymore? 90. Cool, exactly. So that then gives us that, and sorry, this would be N1, and this would be N2, and we've got the ray coming in along this line. But then is it going to refract or is it going to reflect? Well, that's what we're deciding. So we know that theta r has to be 90 degrees for it to reflect instead of refracting. So that gives us N1 sine theta I equals N2. And so we want to know the angle of incidence in this case, which is different to before, because before we had theta I on the outside of the prism, but this time we've got it here. So from before, we found that delta was equal to 14.66. So again, in the chat, who can tell me what theta I is here? $75. Yep, to 2 decimal places, maybe. $75.34. Nice. So once you've kind of scrambled through the wording on this question, this one's slightly more straightforward because this N2 is what we want to find. And we know that N1 is 1.4. And we know that the path it takes has it at an angle of 75.34. And that's equal to N2. So hopefully we then find that N2, which is the maximum refractive index of the fluid, is 1.35. And we know that it's a maximum because total internal reflection only works when N1 is greater than N2. So there'll be a maximum value of N2 above which we won't get this reflection anymore. So I'll just do that. Cool. And nothing in the Q&A. So hopefully that means we can move on to the last question. Question 9. But do keep posting stuff and hopefully I can help, or others can help if there are still bits unclear. So I'll clear all my drawings now. And finally, there's a long bit of information about cat's eyes. But the main takeaway point is that they're a sphere of glass. So for part A, we've got a sphere. I wonder if I can draw that. Yes, amazing. Zoom is so cool. So we've got a beam of light is incident on the surface of the sphere at an angle of 4.58 degrees to the normal of the sphere at that point. if the refractive index is 1.54, what is the angle through which the incident beam deviates as it is refracted at this first surface? Okay, so if we have the light coming in like this, and this is air, and this is glass. So put in the chat, is it going to bend towards or away from the normal? Using Nina's car method. Towards. Yes, exactly. And that's because glass is slower. So this is our angle of incidence. This is our angle of refraction. And so it wants the angle it deviates. So for that, we pretend it carries on in a straight line. And then we have this angle delta of deviation. So first we can use Snell's law, sine of 4.58 is equal to, have we been told? This glass is 1.54. And then sine of the angle of refraction. So from this, we can work out that the angle of refraction is 2.97 degrees. And so if we look at this diagram, we can see that these two lines cross each other. So that means this angle is the same as this angle. So that means that we have theta I is equal to delta plus theta R, which we can rearrange to give us that delta is theta I minus theta R. So 4.58 minus 2.97 gives us delta is 1.61 degrees. And this is where it's key to read the question, because you definitely get points for finding the angle of refraction, but that's not the full story. They wanted the deviation instead. Just the chat. So when at GCSE we said denser material, we meant higher refractive index, basically. Yeah, so I guess the word you're missing there is optically dense, because yeah, an optically dense medium is one with a higher refractive index. So yeah, they mean the same thing. Hopefully, I'm sure one of the other panelists will correct me if I'm lying. So then for part B, we're considering an idealized version where the entire sphere has refractive index n. So that's kind of just as we've done already. And the deflection of the beam inside the sphere will depend on this refractive index. Theta I is the angle of incidence of the beam on the sphere, and theta I is the angle of refraction as the beam enters the sphere. So that's the two we've just done. And we want to know what is the total deflection of the beam once it has emerged from the sphere, assuming it only reflects from the mirror once. So I will just rub out all of this and start again. So this requires a little bit of thought, and you're best just going through it slowly to track the full path of the beam. So we've got it coming in, got our normal here, and the beam coming in. And as you all said earlier, the beam is then bending towards the normal. So if you follow that line, we can see that it hits the back of the sphere. So then reading the question, we see that it says, assuming it only reflects from the mirror once. So there's a mirror at the back that it's then reflecting from. So that means that if we draw the normal here, this angle, which we can call theta for now, it then also emerges at theta. And with only one reflection, we're then going to get it bouncing out of the glass here So now which way is it? Oh, sorry, just check the chat. Yeah, sorry, Catherine's just, yeah, it won't take more than 10 more minutes. If you're happy to stay for a little bit longer. So, okay, I won't ask you, I will just tell you it's bending away from the normal because it's in a faster material. Hopefully you've got that one by now. So right, maybe here. And then let's draw arrows on all of our rays. So it's coming in at theta I, it's refracted at theta R. And now we're going to use a bit of circle geometry because we know that these normals to the surface of the sphere all go to the center. So apologies in advance because these probably won't actually meet at the center, so you have to take my word for it. But that means that these are all radii, which means that this theta here that we've drawn is also theta r, as is this one, as is this one. So now what, oh, and yeah, when it's reflecting out in the same kind of situation as we had last question, because it's coming in at theta r, it will come out at theta I, just via Snell's law again. So now we want to know the total deviation of the sphere. So that it kind of deviates at 3 points. So we'll do them all separately. I think that was one of the hints too. So this is the first deviation. And then if we extend that one, this is the second deviation. If we extend this, this is the third deviation. So then looking at our diagram, we've got that by the same argument as before, theta I is delta 1 plus, sorry, tablet's not working amazingly, theta R. So that means delta 1 is theta I minus theta R. Then here we have a straight line, so 180 degrees, made up of delta 2 plus 2 of our theta R's. So that means that delta 2 is 180 minus 2 theta R's. And then finally, here we've got theta I being made up of theta R. Well, I've got theta I minus delta 3 is theta R. So then we have delta 3 is again theta I minus theta R. So the total deviation would be the first plus the second plus the third. And we want to make sure as well at each point that we're taking it in the same direction to the outgoing ray. So like from here to here, we're going clockwise, same here, same here. Otherwise, our deviations would cancel each other. So the total we're going to get then is 180 minus 4 theta R plus 2 theta I. Back in the chat Q&A. Everybody's happy? It's brilliant. So then finally, assuming that theta I and theta R are small so that the approximation sine theta is theta holds, what refractive index will be needed for the beam that has left the sphere to be moving in exactly the opposite direction to the beam before entering the sphere? So if you're still with us, pop in the chat, what would the angle of deviation need to be if it was going to emerge in exactly the opposite direction? 180? 360? Any other guesses? 360, 360. Okay, so if it was 360, got the cat's eye here, it coming in, it's going to go all the way around and emerge in the same direction, because if we go 360 degrees, we're back where we started. Whereas we want it to emerge in exactly the opposite direction, so it's actually going to come in and go around. Oh, I've drawn 180. I've drawn 360, which is not very helpful. It's going to come out 180 degrees from where it first started. Oh, 3 more things in the chat. Yeah, a few more 180s. So that means that we're going to set delta for this part of the question. For part B, we've got delta is 180. So 180 equals 180 minus 4 theta r plus 2 theta I. So 4 theta r is equal to 2 theta I. So the last little ingredient we need then is Snell's law, which links those two. So Snell's law has n1 sine theta I, but it's in air, so just sine theta I is equal to n2, which we're told is 1.54 sine theta r. And the question's told us that sine theta is approximately theta, so that means that theta I is 1.54 theta r. I think, yeah. So if we then doesn't look right. Yeah, okay. So then for theta r would be 2 times 1.54. 2.08. Oh, I see. Yeah, so we're actually finding the refractive index. I'm solving for the wrong thing. That's why. Yeah, I've lost track of what the question's actually asking for. So yeah, always make sure you write down what the question wants. Actually here, this was theta r, but this is supposed to be just n2 because it's asking us what refractive index. So then, using the approximations, we find theta I is equal to n2 theta r. So then substituting that in, we've got 4 theta r is 2 n2 theta r. So we find that n2 would be 2. And I'll just have a check in the chat, hopefully. Yeah, so Catherine's explained why it's not 360. Yeah, and so is Elle. Brilliant. So hopefully that's everything for this question as well. I will stop showing my screen. And yeah, if you need anything again, then just check for the recording.
Brilliant. Thank you, Anna, for route marching us through that a little bit. But we had a lot to get through and we have almost managed to stay to time. I am going to trespass on your patience a little bit longer because Elle would like to have a go at re-explaining 6C, which was the very last part of the question that she had presenting to you. Elle,
okay, I'm just going to pop it up and you can look back at the recording if I go too fast. Yeah, the things I was looking at weren't super helpful. So we know that the path difference is going to be a half integer wavelength, so 2n plus 1 over 2n plus 1 over 2 times lambda. For lambda to be max, so if we solve for lambda, lambda max would be 2 over 2n plus 1 times the path difference. That's this line here, just solving for lambda. So to maximize lambda, we'll choose n equals 0. That's this line here. So then if we choose n equals 0, lambda max equals twice the path difference. And if we use the same approximation that the path difference is approximately the same order of magnitude as the distance between the two speakers, which hopefully I explained well enough earlier, we can say that lambda max is twice the distance between the two speakers. I think I solved it the other way around, so I just wanted to make that clear here. And that's it. You can go back to the recording and look through that if that's easier. I just wanted to quickly add it in at the end.
That's great, Elle. Thank you. So hopefully if there was anyone who was still a little bit kind of conceptually confused about what was going on in that question, then that would have clarified it. And as Elle said, the recording is already available on the course materials page, so you can go back and watch it as soon as you want to. Go back and check through anything. You can watch it at twice the speed if that's helpful. You can watch it at half the speed, whatever it is that works for you. All right, that brings us to the end of tonight's session. Thank you all very much for joining us. It's been lovely to have you solving stuff along with us in the chat. It's been really cool. We have got 2 more live sessions on the PAT Prep course. We've got one next Tuesday, which is going to be led by Justin, and that's all about circular motion. So do join us live 6:30 till 8 next Tuesday. And then we will have a final workshop session the Tuesday after, where we'll go through the last problems of the course. So as ever, everything's on the course materials page, but you can also get in touch if you need to by emailing us at pat.prep@physics.ox.ac.uk. Have a lovely evening, everyone, and I look forward to seeing you all again next week. Bye, everyone.